Plus, plus. Question. Hey, you want to worry? Your answers on these are just a couple words. So if you're just coming in, you should be able to answer those. If you know how to answer them, you got time. Got about one more minute. Alrighty, that is the end of time. If y'all would please, if you need to write your name, make sure you got your name on there. Otherwise, please pass those up. Alrighty, hopefully that one wasn't too bad. I think On that one, I tried really hard to make it just like a, pulling things out from our last lecture in terms of concept questions. So hopefully those were okay. If you are wondering about the answers to those, it's basically all in the slides from last time. Those are always updated on Google on our Google Drive. And then also the recording from last time is there for you too. Um, so if we have questions about it, I would say try to look up and find those answers first. But then if you go and look them up and you're still unsure about any of those quiz questions, feel free to let me know. Um, so thank you for indulging in that, and let's go ahead and get started. Today we are going to talk about heterogeneous systems. This is chapter 5 in Dr. Spekov's notes. Um, and this is basically how we can deal with the treatment of systems that are very complicated, like a real nuclear reactor has all of these different regions. You've got fuel, you've got moderator, you've got structural materials. So we're going to understand how we can kind of deal with those complexities of a real reactor and do some analytical calculations. Once we do those simplifications, we'll get to a point where we can do some analytical calculations on a reactor. And so last time I posted, I guess at the beginning of this week, rather, I posted homework 4, and I also posted the reactor design problem. What we're talking about today is going to help you a lot with that reactor design problem. Um, so at this point, we've dealt with a lot of very simplified situations involving reactors, right? Like we started looking at just bare homogeneous reactors. We started looking at multi-region systems after that, but they were very simple, like a spherical core surrounded by a spherical reflector. We added some more complexities onto that with talking about like energy dependence, and we started to understand how these quantities like the neutron flux, our cross sections, our reaction rates depend on the energy of the neutron. So with all of that that we've laid the stage for, we're at a point where we can really start to understand a real reactor core. These cores, as we're saying, they have these complex configurations, and that's because these reactor cores are trying to kind of do a lot of different things. You have like your neutronics design, which is you're trying to set up this reactor core so that it's got a critical configuration, so that it's producing power at a constant rate. We know that these fissions produce heat, and that heat is something that you have to deal with, because if you just let the reactor heat up and up and up, then your materials melt and everybody loses their jobs. So we have to have thermal design. We have to be able to make sure that all of the heat that our reactor is producing, that it is able to both move that heat away from the reactor core, but also you have your systems in your reactor to take that heat and then convert it into useful forms of energy. So that's why we have like steam generators and turbines and all of those sorts of things. But the thermal design is super important because your thermal constraints are going to your neutronics are influenced by your thermal constraints. And if you make a reactor that's too hot, then you're never going to be able to build it. There's mechanical design, because these are also like giant mechanical, like it's a big power plant. And so all of these things, you have to make sure that they're like not vibrating, that they're not toppling over. So there's a lot of like structural engineering that goes into making a reactor and setting them up the way that they do. And then there's also the reactivity control, which are all of the different mechanisms that we have in our reactor to make sure that we don't have a neutron population that like goes out of control. We have control rods that can stop the reaction if we need to. We have other things like burnable poisons that we purposely put into our reactor to control the reactivity. And these are all things that, if you haven't heard of them, we're at a point where we can start to better understand them, and we're going to talk about them as we get into understanding real reactors. So there are these neutronics considerations that we're talking about, and these two plots are a kind of good way to illustrate those neutronics considerations. The top right, this is a plot of uranium-238, and it's the absorption cross-section in red, and then it's the fission cross-section in blue. And I pulled both of those right from Janus. So notice that like for uranium-238, we talked about how 238 is basically fissionable, that it only really will fission if it absorbs a neutron that is very fast. And look at this plot. So red is absorption and blue is fission. So if we were to take the ratio of the fission to absorption rate in this low energy, whoops, in this low energy range, notice that the fission down here, we're at an order of like this is like 1 e⁻⁴ around here. Whereas up here, our reaction rate is on, our cross section is on the order of like 10 bars. So we're spanning like many orders of magnitude as we compare the total cross section to the fission cross section. So if it's a low energy neutron, basically no chance that that reaction results in a fission. But as we get to higher and higher energies, notice that once you're basically above 1 MeV, the fission cross section and the absorption cross section are like right on top of each other. That means that basically every absorption will result in a fission if you're at a high energy for U-238. And then bottom plot is uranium-235. And so notice that for 235, it fissions at basically any energy. Basically, any neutron energy, the cross section for fission is very comparable to the cross section of absorption. So if you were to like take the ratio of fission to absorption cross sections, that gives you like a probability that if you have an absorption, it's a fission, and that probability would be pretty high for 235 at basically any neutron energy. But the thing with U-235 is that as you decrease the neutron energy, these probabilities become higher, right? If you compare the cross section for uranium-235 at fast energies, it's like around 1 barn. And then if you compare the cross section of the same nuclide with if the neutron energy is like 10 e⁸ or even 1 e⁻⁷, you're still talking about like comparing hundreds of barns to 1 barn. So you get like many orders of magnitude increase in your cross section. Therefore, the reactions become more likely for a neutron to fission with 235 if the neutron energy is lower. Um, so whenever we talk about uranium fuel, we talk about it needing to be enriched. And the reason that it has to be enriched is because it's only the 235 that is the fissile nuclide. It's only 235 that's going to be able to fission at basically any neutron energy. And if you have 238 in your reactor, what's going to end up happening is that because 238 is so good at absorbing neutrons, as your neutrons are fast and they're slowing down, they are going to probably run into uranium-238 somewhere in your reactor. But these neutrons, as they are slowing down, 238 wants to capture them. So especially in this, notice that in this resonance region, this is like in the slowing down region, these cross section have resonance spikes that also span like a couple orders of magnitude. So especially as the neutron is in the slowing down region, 238 is a very likely thing to make those neutrons be absorbed. And if 238 absorbs a neutron, then it's not causing a new fission. And then we kind of have to worry about, is our chain reaction going to be sustainable if we have too much 238 relative to 235? So ultimately, what we want to happen in our reactor is that the neutrons are born from fission. They slow down in the moderator so that they're not being absorbed by 238. And then they've slowed down in the moderator. They meet fuel again, but when they meet the fuel, now they're at a thermal energy, and it's much more likely that they meet, if they're at thermal energies, it's much more likely that they can meet 235 and make a fission. So in especially thermal reactors, the ratio of your fuel to your moderator is also important because the moderator is going to be the thing that gets your neutrons to a thermal energy. So we can talk about fast versus thermal reactors, and in typical reactors, the uranium enrichment is about 3 to 5%. That's corresponding to what we call low enriched uranium or LEU. So that's about the enrichment that you need to keep a reactor critical for like the lifetime that that fuel is in the reactor. So basically every reactor design requires your reactor fuel to be enriched. CANDU reactors are like the main exception. CANDU stands for Canadian Deuterium Uranium Reactors. This is Canada's like, flagship nuclear reactor that they sell to all kinds of different countries. And these reactors use natural uranium. And they are able to use natural uranium because they use the best possible moderator that you could have, which is D2O. They use like heavy water, so they replace all the hydrogens with deuteriums. Deuterium is basically always scatters and hardly ever absorbs. So the moderating power of D2O is so good that you can basically make a reactor be critical only using natural uranium. And just to go back, natural uranium, when you find uranium in the earth, it's got about 0.7% of those isotopes are 235, and then the rest are 238. So that's a cool thing about the CANDU reactors. Any thermal reactor, so this top right plot, this is showing the lattice of your fuel elements inside of an assembly for a light water reactor or for a thermal reactor. The square lattice is chosen for thermal reactors because we need moderator to allow our neutrons to get to thermal energy. So we have to keep our fuel rods kind of more spaced out, and we have to allow extra space for coolant or for moderator so that our neutrons can get to thermal energies. So like ideally, what happens is that like a neutron is born fast in the fuel, it goes into the moderator, it slows down in the moderator, it has all these scattering collisions that are making it slow down, and then eventually that thermal neutron goes back into the fuel and causes a new fission. So we keep our fuel kind of more spaced out in a thermal reactor to allow for the neutrons to moderate before they go back into the fuel. So that means that the fuel to moderator ratio is really important for a thermal reactor, because if you have all fuel, then you don't get moderation, and you don't cause more thermal fissions. But also, if you have only fuel, then or yeah, if you have only moderator, then you have no fuel. If you have only fuel, then you're never going to get your neutrons to be moderate. So that is like an optimization parameter, is the fuel to moderator ratio for a thermal reactor. And like we were saying, the ideal scenario is kind of what I was illustrating here. You have a fast neutron that's born from fission, slows down in the moderator, meets another fuel pen, and fissions. In fast reactors, you don't need a moderator. They are designed to fission mostly on fast neutrons. And as a result of that, we are able to put the fuel in a more compact form. So basically these reactor cores, they themselves will be more compact as a result of the fact that that we don't need the moderator. So these sorry, I realized I had my wrong slides up. I had the ones with the answers. Um, yeah, so that's also why they use a triangular lattice in these fast reactors, because the fuel is allowed to be closer together because you don't need a moderator. So for this reason, if you have a reactor of like a given power level, like 1 megawatt, the reactor core is going to be because for a thermal reactor we have to have the fuel kind of spaced out. That means that the actual size of that reactor core for a thermal reactor is probably going to be bigger in volume than the comparable fast reactor because of that fuel spacing. So the thermal reactor core will generally be larger in volume than a fast reactor core for that reason. So right now, hopefully, if you have questions about anything I'm saying, please let me know. This is kind of like we're we're assimilating our knowledge, and we're kind of making sure that based on what we've talked about so far, we can start to understand these things in hopefully more detail. So that's thermal versus fast reactors. Um, in general, these systems are heterogeneous. That means that so homogeneous means everything is the same. Heterogeneous means you have lots of different regions that have different things going on. So the kind of hierarchy of the kind of pieces of these reactors is like the smallest thing is the fuel pin. You guys have probably seen those little UO2 ceramic pellets. So the fuel pen, you basically just take a bunch of those pellets and stack them tall, like, maybe a reactor core is going to be like a small reactor core is going to be like about 1 meter tall. a large reactor core is going to be like maybe about 3 meters tall. So imagine you've got all of these fuel pellets and they're stacked in these very thin channels. Those are the fuel elements. And so you've got these pellets that are stacked on top of each other. They are contained within a metal cladding. So that cladding is there to make sure that like any fission products that are born from the fuel don't escape into your coolant, into the rest of your reactor. Um, we place the pellets inside of this cladding and we leave a little bit of gap here so that the pellet isn't like directly touching the cladding. Why do y'all think that we need a gap? Like, um, think about what's going to happen to the fuel. How do we think the size of the fuel is going to compare like at the beginning when we put the fuel in and it's fresh, and then like a year later when we take the fuel out after it's been fissioning for a really long time? How do we think like the size of that fuel is going to compare? Yeah, right. If y'all remember from like 265, you have like swelling, you have these stress induced. Basically, you can almost think of the fission reactions as like putting internal pressure on your fuel pellet. That's basically, and inside of that fuel pellet, you have fission reactions that are resulting in fission products. Some of those fission products are gases. So it's like you had a piece of metal that is inside of your fuel that has fissioned, and now you have these gaseous things that are building up inside of the fuel itself. So both because of heat and like just thermal expansion, it's going to expand, but also because of the swelling as the fuel is burned up, we keep that gap in there to reduce the pellet clad interaction. Um, so that's why there's the gap. We keep all of these elements in these long channels, and then we basically set a bunch of elements up into an assembly. So this is is illustrating the element. There's also like a spring on top, right? And that's because you're pinning all of those fuel elements together so that they don't like move around. You stack a bunch of these fuel elements into assemblies. These assemblies are typically 17 by 17. So like that means that you have 17 by 17 fuel elements in each assembly. And then each reactor core will have like 200 assemblies. So if you take the number of assemblies times 17 by 17, that gives you like an estimate for the number of fuel elements that are in your reactor. All of these fuel elements are fissioning, they're producing heat. And so there's coolant that is like, if my assembly is vertical, there's coolant that's running through the assembly that's passing along the vertical length of all of those fuel elements so that the heat that they are producing is being transferred to that coolant. And then you take that coolant, you make the coolant turn into steam, you put that steam through a turbine, and that is how you convert that heat into useful forms of energy. Um, these assemblies also provide stability because like at some point, this fuel is gonna you're going to use up the fissile uranium 235 that's in there, and you're going to have to either fully pull the assembly out later to basically for storage, or you will reshuffle the assemblies to like assemblies will start at the outer part of the reactor core and they will slowly be moved in as the fuel burns. So you need to take these assemblies out and you move them. That's part of why they're set up the way that they are. But also, you want to make sure reactors are very big. The flow rate through a typical reactor is very fast. And so it's like a turbulent flow configuration going through your reactor core. Therefore, turbulent flows can make things vibrate, can make things like kind of move around. And so these fuel assemblies are also designed so that it reduces like vibrations and things like that that could be caused because of the fluid moving past them very quickly. And so they help for stability. They also help for your fluid flow and your heat transfer. You'll have these little like spacer grids that are placed at various, like if you look at the axis of an assembly, you'll have these little spacer grids at different points. And those spacer grids are designed to like trip up the flow and add more turbulence to the flow so that, because more turbulence allows for more mixing and that allows for better heat transfer. So there's kind of a lot going on. Like when you see this assembly, it might look simple, but there's actually like a lot of details behind why we set these things up the way that we do. This is just like a table of some typical reactor designs. So different kinds of pressurized and boiling water reactors, and then a couple different gas, like fast reactors. So kind of like what we were just talking about. Well, there's a lot of stuff in here that we could make use of and that we could use to like better understand. Question?
Say hypothetically that we have to find certain kind of Westinghouse reactor.
Mhm.
How would we find certain things you might be finding?
The thing to look up, so where this would all come from is called the design control document. So any reactor that you want to build, you have to go through. And the thing that's cool about like the AP1000 is the newest reactor to go through like the full licensing process with the NRC. So they've already submitted all of these kinds of documents to the NRC to verify everything that the NRC wants them to verify about their reactor operating safe in every possible condition and yada yada yada. So if you look up the AP1000 design control document, that's where you could find this kind of information. Um, yeah. Um, so, um, to consider a reactor type to be heterogeneous, we actually have a very simple criterion called the heterogeneity criterion, and it's all based on the mean free path, kind of like how far do neutrons travel as between interactions as they're moving through your reactor. So we've already seen how to calculate the mean free path as like 1 over the total cross section. So that's this definition, and that's what we have already seen. Um, Sometimes we will introduce the transport mean free path, which is a very similar definition to the regular neutron mean free path. It's just that instead of doing 1/sigma total, we do 1/sigma transport. And the transport cross section, which is sigma subscript TR, that's the transport cross section. It's defined as sigma total minus this thing called mu0 bar times our scattering cross section. So our transport cross section is the total cross section minus this scattering cosine times our scattering cross section. And what that mu0 bar times the sigma s does is it basically provides a correction factor to the total cross section to account for any possible anisotropies that are going to occur as a result of like the scattering process. So the way that this mu0 bar is defined, if you assume that it's S-wave scattering, you can get an analytical expression for mu0 bar, and that expression is 2a, oops, 2a over 3. Shit, sorry, it's 2/3a, my bad. 2 over 2/3a, where the 3a is in the denominator. Um, So in A, we had introduced this big A last time. It's the ratio of your the mass of the nucleus to the mass of the neutron, and A is about the same as the atomic mass. So we use the same symbol, and you can actually use atomic mass for A. In my class, feel free to do that. If it's a real reactor problem, A is more precisely mass of the nucleus over mass of the neutron. But nevertheless, if you have um, so basically, like in terms of this transport cross section, if you know the nuclide type, then you can approximate mu0 bar, and then if you have the total cross section, you can get the scattering cross section, and then you can find the transport cross section. If you're not given information about like the nuclide to find mu0 bar, or if you're not given information about the transport cross section, you're okay to assume that the transport cross section is just the total. But in some contexts, if we have the information, we can compute the transport cross section. We could talk about the transport mean free path as well. And so basically, if a reactor is heterogeneous, then it means that the mean free path at any neutron energy is either less than or comparable to the characteristic dimensions of the fuel element in our reactor. So what we're saying is that for all energy, this is basically saying for any energy E, the mean free path, so this is like the total mean free path. is always going to be less than or equal to the mean free path for transport. And that is going to be less than or equal to your characteristic fuel element dimensions. So this right here is what we call the heterogeneity criterion. If we think about the transport mean free path to the total mean free path, notice that the transport cross section is always going to be equal to or less than the total cross section, right? Because it's total minus this thing. So like if mu zero bar is 0, then the transport cross section is equal to the total cross section, and then their mean free paths are the same. But if mu zero bar is non-zero, then the transport cross section is going to be a little less than the total because you're subtracting this thing off. And then if the mean free path is 1 over that quantity, well, the transport cross section is always going to be smaller, therefore, or equal to the normal mean free, sorry, the transport cross section is always going to be smaller than the total cross section. Therefore, if you do 1 over, then, which is the mean free path, that means that the mean free path for transport is always going to be bigger than the mean free path for total interactions. And basically what we're saying here is that the mean free path represents the number of collisions that you have per unit. It represents the average distance that you go per collision. So if you have some distance that you're going per collision that's less than the characteristic fuel dimensions, then you might not even have one interaction inside of that part of your reactor. So if you basically need your mean free path for a reactor to be considered homogeneous, you need the mean free path to be less than the characteristic fuel element dimensions so that the neutron can have multiple interactions while it's inside of that fuel element. Yeah.
Has to be less than the transport.
So by definition, the mean free path for transport is always going to be bigger than the total. And that's just because of these definitions. So like if I added numbers, it would be easy to see. So perhaps it would be helpful to just do a quick example. And actually, I'll just keep this here and I'll just throw it on. Oh, shit. That's fun. Sorry. So I did a bad thing, which is that I erased the text that I had put, but it's fine. Um, I'll put the text back so that whenever we are looking at this later, we won't be looking at a blank slide. Um, so we we had filled that in, and basically what I was trying to show. Just pull this up real quick. So let's just say for as an example that sigma total was 10 centimeters to the minus 1. And then let's assume that that mu 0 bar is, let's just make it easy and make it 1. And then, oh yeah, sorry. So sigma total is about 10 centimeters to the minus 1. Let's say mu 0 bar is about 1. Let's say sigma s is also about 1 centimeters to the minus 1. So if we were to calculate sigma transport, then it's sigma total minus mu 0 bar times sigma s. So what does that mean that my transport cross section is going to be equal to? Yeah, perfect. 9 inverse centimeters. And so notice the transport, if I think about sigma transport versus sigma total, the sigma transport and the sigma total could be equal if this term is 0, but usually mu 0 bar isn't going to be 0. Therefore, you're going to have some number here So then how does sigma transport have to always compare to sigma total? Greater than or equal to or less than or equal to? Less than or equal to, right? It's always going to be less than or equal to the transport cross section because you're taking the total and then subtracting some away. So the transport is always going to be either less than or possibly equal to the total if mu zero bar is zero. And so if that makes sense, then we can think about the mean free path, for the total, and then the mean free path for the transport cross section. So how would I get the mean free path for the total cross section? Perfect, 1 over sigma t. And then we know sigma t is 10, so then the mean free path for the total is going to be 1 over 10, which is 1/10. And what's the units of mean free path? Centimeters, right? So that's what the mean free path, the total mean free path corresponding to the total cross section would be. And then how do I get the mean free path for the transport cross section? Perfect. Yeah, it's just 1 over that cross section. But the transport cross section was smaller. So instead of having, so this is 1 over 9. So we can say 1/9. So notice the transport cross section was smaller, but the transport mean free path is larger because it's the reciprocal. Because you're doing 1 over. So if this thing is small and this thing is large, and you're doing 1 over a small number, that result is going to be bigger than this. So that's why we're saying, like in that first part of the inequality, is that mean free path total is always less than or equal to mean free path for transport, but then the mean free path for transport is always less than or equal to those characteristic dimensions of the fuel. So yeah, hopefully if that was confusing at first, hopefully that clarifies, and that was what I was trying to say about the arguments about one being larger or smaller than the other. Okay, and like I said, I'll fill those. Oh, question?
We've been to make sigma transport same as sigma total because uranium's rather large A, so
Yeah, for a lot of these nuclides, we are basically assuming that's a good point. Yeah, like if it's a small nuclide, that's when we're going to have mostly elastic scattering. If it's a large, and in which case, but yeah, if it's a large nuclide, then yeah, A is going to be very large, so mu zero bar is going to be very small. So for the purposes of what we've been doing up till this point, we haven't really needed to distinguish that much between like the regular transport, the total and the transport cross section. But now that we've discussed scattering, it kind of fits in to make that more to just basically give a more precise definition for the transport cross section. So this is, I guess, another example that could help us just understand what does it mean, like if our system would need to be considered heterogeneous or homogeneous. So we want to consider a system, and yeah, so this is kind of what I was just saying. If you have a mean free path of 1 centimeter, you have a transport mean free path of 1.1 centimeter, and then the diameter of your fuel pen is 1.5 centimeters. So in this case, if the neutron goes inside of the fuel pen, on average, is it going to have at least one collision with inside of the fuel pen?
Yeah.
Right, because its mean free path which is the distance it goes per collision, is less than the dimensions of the fuel pen, right? If my mean free path is 1 centimeter, that means every 1 centimeter that I go, I'm going to have an interaction. And if my diameter is 1.5 centimeters, then it's a pretty good chance that I end up having at least one interaction in that fuel pen. So absolutely, yes, it would. And does that mean that we have to consider the reactor as heterogeneous or homogeneous? Yeah, perfect. This meets the heterogeneity criterion. So it's a heterogeneous system. So the reason that heterogeneity is important is that if you have a heterogeneous system, your flux can change quite considerably as you go from one region to another. Um, and like, especially if you're going from your fuel into your moderator. So for heterogeneous systems, we have to take this into account. Generally for thermal reactors, the mean free path is about 1 centimeter. And so that is going to be less than the characteristic fuel dimensions. So if you have a thermal reactor, it's going to be a heterogeneous system and you have to treat it that way. That makes the modeling of a thermal reactor a little bit harder than it is for a fast reactor. Because for a fast reactor, the mean free path is like anywhere from 10 to 50 centimeters, which is going to be larger than the characteristic dimensions of your fuel pens. And that means we can treat fast reactors as homogeneous systems. It means that in a fast reactor, as you go from like the fuel to the coolant, the flux isn't varying nearly as much as it would if you were talking about a thermal reactor going from its fuel to its moderator. So that means that when we model a fast reactor, it's actually a lot easier. Um, and so if you have a homogeneous system, you can simplify the fuel and lattice and these different regional effects by just kind of like averaging everything out in a very simple way. If you have a heterogeneous system, you can still average things over, but you have to account for differences in the flux from region to region, which makes the calculations and the treatment, it makes the calculations harder, and it means that you need a more detailed treatment if your system is heterogeneous. So this is a plot that we've kind of seen this plot before, and this is just showing a absorption cross section for a typical nuclide, like a fuel nuclide. What we have been seeing is just like the plots that we were seeing for like uranium-235, right? The absorption cross sections are very high in the thermal region, so that's the region where our neutron is like most likely to be absorbed. Um, but in the intermediate or in the slowing down region, we have those resonance spikes. And so that's another place where our neutron could get captured. And that's where uranium-238 in particular is very likely to parasitically capture our neutrons when it's in that resonance region. And then in the fast region, our absorption cross sections are pretty low. So most neutrons are born fast. At the fast energy, the absorption cross section is low. So it's very unlikely that a neutron is born fast and it gets absorbed in the fuel. What's more likely is that it escapes the fuel, it moves around, and then it meets another fuel another fuel pin sometime later. So that's just kind of like the variations of these cross sections in each region. And just like we can break up the energy into different regions and say we've got like a fast and an intermediate and a thermal region. We can also break the flux up into those regions, just like we did with like multi-group diffusion. And so what I wanted us to do is kind of take that understanding and think about if we had like an infinite fuel and moderator lattice, what would the behavior or like the plots of our three group fluxes look like? So we're going to have a fast flux, which is phi1. We're going to have a resonance or an intermediate flux, which is phi2. And we're going to have a thermal flux, which is phi3. And we want to sketch what these fluxes look like in our system. So let's start with a fast flux. And let's ask the question, so the fast flux is my flux of neutrons who are in the fast energy group. where are my fast neutrons going to be born? They're born in the fuel, right? So it kind of stands to reason that if I were to draw the graph of my fast flux, where should it have a maximum? In the center of the fuel, right? And so if I think about the fast flux, it's going to have some maximum in the center. And then as I go outside of my fuel, there's going to be less fissions happening, which means there's going to be less fast flux. So we can hopefully imagine that this fuel, the fast flux, is just going to kind of slowly diminish as you get into the moderator. At some point, the fast flux, so this is an infinite lattice. And so just like we have fuel here, we also have another fuel element here, and we have another fuel element here. So like kind of a similar thing where the peak that this, actually, this is not great. So the peak of this fuel region is going to be somewhere over here. So we're almost imagining like this peak is coming down. And basically these fluxes are going to meet. This is the fast flux being continuous. So if it goes to like some minimum in the moderator and then a maximum in the fuel, it's kind of going to keep doing that, right? It's going to reach your minimum in the moderator, and then it's going to be at a maximum when it gets to this next chunk of fuel, and it's going to have a trend that looks kind of like this. So this is phi1. That's the fast flux. It peaks in the fuel and then it decreases as you get to the moderator, and we have an infinite lattice, so we kind of get this repeating sinusoidal function. Hopefully that makes sense, just based on the fact that neutrons are born fast. As they go into the moderator, they're either going to be slowed down, in which case the neutrons are going to be knocked out of the fast group, and that's why the fast flux is decreasing, or they're going to be absorbed, in which case they're gone, in which case that's also why the flux will decrease. So if the fast flux peaks in the fuel, where do we think the thermal flux is going to peak? In the moderator, right? Because once the neutrons get into the moderator, they're slowing down. So as I get into the center of the moderator, my thermal neutron population should increase. So if I make a sketch for my thermal flux, let me use purple. It's going to basically do almost the opposite, that the thermal flux is going to peak in the moderator, and then my thermal flux is going to decrease as I get into the fuel. The thermal flux is going to have a minimum in the fuel because in the fuel, that's where my thermal neutrons are going to be absorbed. They're going to cause new fissions that are going to make more fast neutrons in the fuel. So the thermal flux, which is what I'm showing here, almost has an opposite trend as the fast flux. So this is phi3. This is the thermal flux. And hopefully that makes sense too. Peaks in the moderator, because that's where neutrons are slowing down the most. It's at a minimum in the fuel, because that's where all my thermal neutrons are being absorbed to make new fissions. The only other one that we need to sketch is the intermediate range. And the intermediate range is kind of funny. When we are in that intermediate or that resonance range, basically as a consequence of what's happening with elastic scattering in the moderator, the resonance region is basically flat. But then, like we were seeing with those peaks of the resonance region in the absorption cross section of my fuel, when these resonance range neutrons get into the fuel, they get very quickly absorbed. So what the resonance flux looks like is that it's basically flat in the moderator, and then it quickly diminishes as I get into the fuel. So it basically drops off, and that's why I'm not continuing it anymore, because the intermediate or the thermal flux will actually basically stop at a certain point in the fuel, resulting from the fuel preferentially absorbing or parasitically capturing the neutrons that are in the resonance region. Yeah. Mm-hmm. And so that is kind of like the way this illustration right here, especially for the for the resonance or for the intermediate flux, notice that it's like as my intermediate neutrons go into the fuel, they basically get absorbed by like the outer fuel atoms, and the fuel atoms that are in the middle of the fuel don't really see hardly any of the intermediate flux. So the outside fuel kind of like self-shields the fuel on the inside from the intermediate flux. And this is an example of what we call spatial self-shielding. Spatial self-shielding. The fuel is like kind of shielding itself from those thermal neutrons, um, such that the fuel in the middle doesn't really see much of the thermal flux compared to the fuel atoms that are like on the outside of that fuel pin. Question?
This fuel moderator device is just a cross section of an assembly or
Yeah. Basically, what you would imagine is, yeah, exactly. Just like,
fuel L.
yes, yeah, this is like a fuel element, and then yeah, exactly. And this is just showing it in 1D, but like you could also imagine that like it would look the same way in the in and out of the page. But yeah. All right. So, that's a good illustration to have about what those different flux components, what our different group flux components would look like in a infinite fuel moderator lattice. And hopefully that makes sense. Hopefully we can reason why those plots look the way that they do. Um, so the next thing that I wanted us to do is develop the 4 and the 6-factor formulas. Um, I don't know if y'all have seen the 4, or I'm sure that y'all have at least seen those before. I don't know if y'all remember like where they come from. So I wanted to like kind of review that. We have or we haven't?
Definitely have.
Okay.
Hope so.
Okay. Then this will hopefully be a review, and helping, this is going to help us to better understand, because basically these 4 and 6-factor formula terms, we can think about them differently if we have a heterogeneous versus a homogeneous system. So I wanted to like review the 4 and 6-factor formula and then talk about how heterogeneity effects play a role in these terms. So to get these formulas, we basically define a bunch of probabilities that describe what could happen to a neutron in a reactor as it goes from like being born in fission to all the different possible interactions it could have as it tries to, as the neutrons born from fission try to cause a new fission to happen. So first thing we define is PFNL. The FNL stands for the fast non-leakage probability. So it's a probability that a fast neutron doesn't leak. It's a non-leakage probability, so it's a probability that a fast neutron doesn't leak. Similarly, PTNL is the, oh shit, that's supposed to be thermal. Sorry about that. T and L is the thermal non-leakage probability. F and L is the fast non-leakage probability. So as the name suggests, it's a probability that a thermal neutron doesn't leak. Little p is the resonance escape probability. So it's basically the probability that a neutron is not absorbed while it's slowing to thermal, assuming that it didn't already leak. So given that it didn't leak. So that resonance escape probability has to do with like that intermediate flux that we were talking about, and the intermediate flux likely being absorbed, the neutrons in the intermediate flux being like absorbed by the fuel. We call those resonance captures. The resonance escape probability is that the fast neutron does not get absorbed while it's slowing down. The thermal utilization is basically the fraction of your thermal neutron absorptions to your total neutron absorptions. So it's the probability that the thermal neutron is absorbed in the fuel, given that it was absorbed while it was thermal. Given that it was absorbed while thermal. U sub F is the fast utilization. So that's the probability that a fast neutron is absorbed in the fuel, given that it was absorbed while it was fast. So given that it was absorbed while it's fast. And then we have two more probabilities. PTAF is the probability that a thermal absorption in the fuel causes fission, so that a thermal absorption causes fission. And then PFAF is the fast version of that. It's the probability that a fast neutron absorption causes fission. And then we have a nu T and a nu F, which is the number of neutrons born from thermal fission and the number of neutrons born from fast fission. So with all of these probabilities, we can start to develop like kind of a probability tree that's going to show all of the possible things that a neutron can do. And we're going to have different branches for what the neutrons can do. Along each branch, we'll assign a probability, and then we'll follow these branches all the way down. We'll multiply the probabilities that corresponding to things making it all the way through this process. And that's where these 4 and 6 factor formulas are going to come from. So the neutron life cycle starts at the top, and it starts with neutrons that are coming out of fission being born fast. So if a neutron is born fast from fission, the first thing that it can do, it kind of has 2 main possibilities for what its life is going to look like. And this fast neutron, it's moving very fast, so it can either stay in the reactor or it can leak out of the reactor. So we're going to say that this down here corresponds to doesn't leak. And we're going to say that this branch off to the right is that the reactor leaks while it's fast. What's the probability that we don't leak while we're fast? PF and L, right? So that's what this line corresponds to. This line is a probability that corresponds to PF and L. And if PF and L is the probability that it doesn't leak, what is the probability that it leaks if those are my only 2 options? 1 minus, right? Yeah, it's just going to be 1 minus P, F, and L. And once the neutron leaks, we don't care about it anymore. It's not going to cause a new fission. So the probability tree dies right here. The tree no longer continues because the neutron is now gone from our analysis. So now we have a fast neutron that hasn't leaked. If the neutron is fast and it's moving around in our reactor, it is either going to be absorbed while it's fast, or it's going to slow down to thermal energies. So I'm going to say that this over here corresponds to slows to thermal. And I'm going to say that this arrow right here corresponds to being absorbed while fast. Right? If I stay in my reactor, if I don't leak and I'm fast, I could either be absorbed as a fast neutron, or I could have some scattering collisions that slow me down to thermal. What's the probability that a fast neutron slows to thermal without being absorbed? PFNL was the non-leakage probability. This is the probability that the fast neutron isn't absorbed. P, right? It's just the resonance escape probability. Perfect. P. And if P is the probability that it slows to thermal, what has to be the probability that it is absorbed while fast? If I have P probability of going this way, what's the probability that I go the other way? 1 minus P, right? Because these probabilities, like my only options are either to do this or to do that. So the total probability has to be 100%. And if like 30% is P, then the other 60% has to be 1, or 70% has to be 1 minus P. Okay, so now over here, I've slowed to thermal. And as I'm slowing to thermal, I kind of have 2 options. A neutron that is slowing to thermal could still leak while it's slowing. So one option is that it leaks. the other option, while it slows to thermal, which is hopefully what we want to happen, is that it gets absorbed while thermal. So that's the other option, is that it gets absorbed. And so now, what's the probability that we get absorbed while we're thermal? Yeah, that was the PTNL. And if this branch is PTNL, then this branch right here has to be 1 minus PTNL. But ultimately, that's a leakage. So that part of our probability tree is going to die right there, because once the neutron leaks, we don't really care about it anymore. So over here, so now we kind of have two branches. Going this way, this is our thermal branch. And then going this way, this is our fast branch. And so over here, we were saying we could be absorbed while we're fast. If we are absorbed while fast, there's two things that we could be absorbed into. We could either be absorbed into fuel, which is what we want, or we could be absorbed into something else like the structural materials or the cladding. So we either say absorbed in fuel, or we'll say absorbed in junk. And the junk could be like the clad, it could be the maybe you have like some in-core detector, maybe the neutron gets absorbed in that. So if we are absorbed in the fuel while fast, what's that probability? UF, perfect. And then this is 1 minus UF. And so continuing from the fast branch, we were absorbed in the fuel. So if we're absorbed in fuel, we have two options. Either we're absorbed in the fuel and we cause a fission, or we're absorbed in the fuel, but we don't cause a fission. So this is going to be fissions, and this is going to be does not fission. And if we cause a fission while absorbed in the fuel and fast, what was that probability? Perfect. Yeah, this is going to be PFAF. And this is the fast branch. So after we fission, we are going to produce new fast neutrons. So new F is the number of fast neutrons that are going to come out of this process. And so these new F fast neutrons go back and they start the process again. This is a new generation, and then we could follow the probabilities again. So we've completed the fast branch, and then we need to finish the thermal branch too. Just like in the fast branch, when we're absorbed as a thermal neutron, we can either be absorbed in junk, in which case the neutron is gone and we don't care about it anymore, or we get absorbed in fuel. We'll say absorbed in fuel. And if we are absorbed and we're absorbed in the fuel while thermal, that was our F. That was our thermal utilization. And then once we're absorbed in the fuel, we could either fission or we could not fission. So this is going to correspond to fission on the left and then not fission on the right. And if we are absorbed and we cause a fission while thermal, that probability was PTAF. And in the thermal branch, if we cause a fission, then after that fission, we produce new new thermal neutrons. New T is the number of thermal neutrons that get produced. Question?
Why is fast in the language you have thermal utilization?
Good question. Just to keep us on our toes. Yeah. Yeah, it's one of those things where like nuclear engineering isn't that old of a field. Like it's only, started like mostly in the 60s in terms of like actual power reactors. So I feel like a lot of the terminology hasn't really updated much since then, and maybe it was like we were just trying to come up with something so that we could build some reactors, and then we didn't really realize that like along the road people were gonna wonder about how to do this themselves, and they're gonna think this doesn't make any sense. I would not have set it up this way. Um, But yeah, so like when we had defined K effective, we had defined it in several different ways, but one way that we defined it was like the number of neutrons born in one generation divided by the number born in the previous generation. So like this kind of approach is how you could think about that. That this is the first generation, you have all these things happening, you keep track of all of the probabilities, and like ultimately there was only one branch that survived all the way to the end. So like basically if I multiply all of these corresponding probabilities of all of the branches that were successful, though that product of all of those probabilities is going to correspond to effectively the number of neutrons that come out of one branch. And then also if I follow the probabilities the other way of the probabilities that all survived to make a new to repeat the cycle, those are the things that I would multiply together to figure out how many neutrons came out of this process. And so if you do that multiplication, if you multiply all of those corresponding probabilities, you basically get two terms because you're adding up the thermal branch and you're adding up the fast branch. So if you add up the thermal branch, you're going to get both of them have a P, F, and L. And then part of the thermal branch, we had a resonance escape probability. We had P, T, and L. We had the thermal utilization. We had PTAF, and we had nu T. So those were all of the terms that we had on our thermal branch. And then we had the fast branch too. And the fast branch had P, F, and L, and then it had 1 minus P. It had UF. It had PFAF, and it had UF. If you look at the tree that we just drew, this should be all of the probabilities multiplied along the left or the thermal branch. These should be all the probabilities multiplying together on the fast branch. And these are just the probabilities that make it all the way down the tree.
Wait, yes, you have pause.
This is nu T and this is UF.
Oh, you
Oh, yes, sorry, you're right. I have a typo in my slide. This should be a nu right here. Right? Yeah, thank you. And then by definition, these terms actually get grouped together so that PTAF and the nu T, we lump that together and call it eta thermal. And then we lump the fast corresponding terms together and we call that eta fast. Um, and so because we have these two branches, we want one equation. So we define this epsilon, which is called the fast fission factor. Epsilon is the fast fission factor. And this is basically defined so that we can combine all of these terms into like a single equation. It's basically defined such that we can make these substitutions into our six-factor formula, and we can get one equation. And if you plug all of that in, you get P, F, and L. You get the resonance escape probability P. You get P, T, and L. You get the thermal utilization. You get eta T, and you get the fast fission factor. So that right there, that is the famous six-factor formula for the multiplication factor. And it's just six probabilities that are multiplied together. Two of those probabilities, which of those probabilities relate to leakage? And if we have no leakage, like if we have an infinite medium, then there's no leakage. So what does that mean about PFNL and PTNL if it's an infinite medium? Both of them are one, right? The probability that we don't leak is 100% if we can't leak. So then PFNL becomes one, PTNL becomes one, and then the four-factor formula for K infinity is just everything that's left over. It's P times F times eta T times epsilon. So that's the famous four-factor formula for the infinite multiplication
That-
factor. Yeah, that's sorry, no, that's eta. Um, sorry, yeah. And yeah, this is supposed to be an eta too. Just sometimes my etas look like some weird cross between a U and an N and a V and sorry. Oh,
Okay,
so
sorry.
no, so eta is here and eta is here. Oh wait, sorry. This is my eta, and it came from this step. I was substituting in, and it's another thing where my eta looks really bad, so it kind of looks like a U. Sorry about that. I can try to make that clearer. Those were both eta. Hopefully that's better.
So it's the average number.
Yeah, it's the neutrons produced times the non-leakage the TAF or the FAF depending on yeah. Mhm. All right. So we had already done the multi-group diffusion model. And we had the question on our exam, which was like, and we had the homework question deriving like K effective and the group fluxes for the two group model. You can also use that same two group model to come up with approximations for all of these probabilities. It shows how you can do these derivations in section 4.2. So if you wanted to make the connection between what we've just done with these different probabilities and how you might actually try to calculate them for problems that we've already seen, that's the approach that we could use to do that. So that's mostly just a for your information kind of thing to connect with what we've already talked about. The next so we did all of this so that we could start talking about how these different terms in our four-factor equation, how we can think about them when we have a heterogeneous system. So this is a plot that's showing all of these factors as a function of x, where on this x-axis, x represents the fraction. It's kind of like the ratio of fuel to moderator, that when x is 0, that means that we have no fuel and only water. And then as x increases, we're increasing the number of uranium atoms per H2O molecule. So like when x is 1, it means that we have, and I guess this is probably a fraction, because if you went all the way up to 100, that would be like 100%. So yeah, I mean, it's kind of like a fraction. It's like how many uraniums do you have per number of H2O atoms. So generally, going to the right, it means that we have more fuel. Going to the left, we have less fuel. So if F, that thermal utilization factor, is the number of absorptions in the fuel divided by the total number of absorptions, then notice how when X is 0, F is 0, and as X increases, F increases too. We could see F increasing as X increases. And hopefully that makes sense that as we're adding more fuel, we allow for there to be more absorptions in the fuel. So therefore, F goes up as X goes up. P, that's our resonance escape probability. So notice that P actually goes down as X goes up. And that kind of makes sense too, because if we think about increasing X, that means that we are adding more fuel and we're taking away the moderator. And if you have less moderator, then you have less neutrons able to get to thermal energies. Therefore, you have less that are able to get there before they're even absorbed. So as X goes up, the resonance escape probability goes down, basically you are yeah, you're increasing the chance that you get some kind of resonance absorption in the fuel if you have more fuel and less moderator. And then epsilon is that fast fission factor. You can also think of it as 1 plus the number of fast fission neutrons divided by the number of thermal fission neutrons. So notice epsilon increases as x increases, and that probably makes sense too, because if we have more fuel, then we have more fast fissions, more neutrons coming out of fast fissions. Also, more fuel and less moderator means less thermal fissions. So the number of fast fissions is going to go up, the number of thermal fissions is going to go down. So epsilon is going to increase as x increases. And as a result of k infinity being a product of these three probabilities plus eta, but eta is kind of more complicated. To know eta, you kind of have to know like your whole flux distribution. So we don't really talk about eta so much as we talk about epsilon, f, and p. But because epsilon and f are going up as x increases, but p is going down as x increases, you kind of get you get a maximum, and you get two possible values of k infinity that correspond to a critical configuration. So this is a similar plot. This is showing k effective as a function of the fuel volume fraction for a reactor that's basically, it's a reflected spherical reactor that has a total radius of 1 meter. So that means that the fuel volume fraction here, it's just of this 1 meter reactor, what fraction of the volume is the fuel and what fraction of the volume is the moderator. And this is plotted against several different moderating types. Notice that, so at x equals 0, basically all of these are 0. That corresponds to, like, we have all moderator, so not really much k effective going on if our reactor is just moderator. And then as we go up to x equals 1, that corresponds to a reactor that's all fuel and no moderator. And this plot is really interesting because it shows the importance of moderators that have hydrogen and the ability of K effective to both have a maximum, but also if you read the plot right to left, if we read right to left, we're decreasing the amount of fuel in our reactor. But notice that if you have a hydrogen bearing moderator, then you can decrease the amount of fuel in your reactor, but actually increase K effective along the way. And this is a function. The reason this happens is because when you're comparing moderators, there's like the figures of merit we talked about last time, like the moderating ratio and the moderating power and squiggle and the average number of collisions to get to a thermal energy. And all of those metrics might make you think that graphite is the better moderator because it's going to have like better moderating ratios and things like that. But the issue with graphite and the issue with these other non-hydrogen bearing moderators is that their mean free path is very large. So if I have, like, for example, in graphite, if I have a large mean free path, it means that the neutrons go a large distance between collisions. So like if they need 50 scattering collisions to get them to a thermal energy, but they travel like 10 centimeters per collision, then it means that you need a very large amount of graphite for these things to be able to bounce around and to have enough collisions that result in them becoming thermalized. So it's a thing where the mean free path actually matters. And because the mean free path is so large for these non-hydrogen bearing moderators, by the time you have enough fuel to be critical, it's like you're basically critical on a spherical, like on a bare reactor. You like haven't added enough moderator to get the moderating ability or the moderating like effect that you need without there being enough of that moderator there. So I wanted to show this plot because it's an interesting one to kind of think about different things about a moderator, different parameters, not just those figures of merit that we talked about, but also thinking about how like the mean free path and the total and the total cross sections would impact our moderator design. It basically means that if you want to design a reactor that's space constrained, like, size constrained, and that's the thing with this reactor, they're trying, in this paper, they're trying to design a micro reactor that's 1 meter cube, like 1 meter radius. So they are size constrained, and it turns out that if you want to have a small reactor, these hydrogen bearing moderators are kind of the best ones. Yeah,
Reactor design process.
it's a fast reactor, so there's no mod. Yes.
So, I mean, generally, we want to be to the right, right? For safety. I would think, light water reactors.
Yeah, I think so. Because if you have less fuel, that's generally gonna mean that, like, there's a thing that they talk about, which is the source term, which is kind of relating to like the total amount of fissile material that you have in your reactor, as well as like the power density. So yeah, like even just like from a cost perspective, right? We would probably want to make the reactor that has K effective of 1, because that's going to be able to get us critical with like the smallest possible fuel volume fraction. So it's going to mean like less fuel cost if we pick some configuration on the left side of the peak versus on the right.
I was just thinking in terms of like, what,
Yeah, that's what I was meaning in terms of like the source term. Like the amount of fuel that's there is going to affect your source term, which is going to affect like basically how much do we have to worry about this reactor if it has like an accident. So yeah, if there's less fuel, then you have less of a source term, and it means you also have less concerns. But yeah, the point about the thermal is valid too.
I would just feel more.
Yes. Yes, absolutely. Um, they gave me, when I did my qualifying exam, this was one of the questions that they gave me and that they asked. It was like, for this plot, explain why there's a peak for the hydrogen containing moderators and there's no peak for the other ones. So hopefully that kind of makes sense. Like I'm trying to explain this the same way that I explained it in my QE, mostly just based on the stuff that we've talked about in this class. So moving forward. So when we think about heterogeneous versus homogeneous configurations, I wanted us to think about how to picture that. And then I wanted to talk about what the choice of, or what the configuration heterogeneous versus homogeneous tells us about our different terms in the six-factor formula. So like a heterogeneous configuration is like the detailed treatment of the fact that this system has different parts. So like if you're looking at like a lattice of fuel elements, you've got fuel, they're surrounded by cladding, and then you've got a coolant and moderator. Each of these regions is distinct. Each of these regions is going to have different cross sections, different material properties. When we talk about a homogeneous configuration or homogenizing a reactor, it's like we're taking this configuration and we're putting it in a blender and we're kind of like smoothing out or averaging out, or like, to the extent that there are differences in the material properties, it's like instead of those things having specific places in our reactor, it's like everywhere in the system it's a average of all of the different properties that were there. So it kind of like averages out or like doles the effects of any individual pieces that would be in our system. It also means that we don't have as much spatial effects because of like the fuel isn't concentrated in these regions. The fuel is now like equally distributed across the reactor. So whereas all of the power would be concentrated in these fuel spots, now the power and the fuel is like distributed around. Same thing with the moderating. Like in the heterogeneous configuration, only moderator exists here. So neutrons that are passing through this part of my reactor are going to be significantly slowed down. They're not going to be doing much absorption because they're not interacting with the fuel while they're in the moderator. And when you have the homogeneous configuration, it's like at every point, no matter where you are, you have some moderating effect because you've smudged out all of these cross sections so that the the moderating ability is kind of uniform over the reactor, the fuel is uniform over the reactor, and these sorts of things. So basically, as you homogenize something, any regional differences in your material properties and what happens in each region gets diminished. So what I wanted to do was talk about how these four-factor terms, how to think about them if we have a heterogeneous versus a homogeneous system, and in which situations these quantities will be larger or smaller. So if we think about the resonance escape probability, the fraction of neutrons that manage to slow from fast to thermal without being absorbed. For neutrons to make it to thermal energy, they need to slow down in the moderator without being absorbed in the fuel. So if we want to know which configuration has a higher resonance escape probability, I think the main question to answer is just which configuration is going to give us more moderation. Because the configuration that gives us more moderation is going to get more neutrons to thermal energies and is going to correspond to a larger resonance escape probability. So which of these configurations, the heterogeneous versus the homogeneous, is going to allow for more moderation? We think homogeneous? Is that what we both said?
I was going with the
Okay. If you guess 50-50, then you've got a 50% chance. So what we were saying before is that if it's homogeneous, then any regional differences are diminished. So what that means is like in the center, right? It's all moderator here. So if I'm in my heterogeneous configuration and I'm a fast neutron moving through the center of this heterogeneous configuration, then I'm going to experience a lot of moderating because I'm only moving through moderator. And like as I'm in this region, there's no fuel or cladding or anything else. Whereas if I'm in the homogeneous configuration, everywhere is kind of the same, both in terms of its moderating ability, but also like all the other effects are going to be there. So the thing about this is that if I want more efficient moderation, if I want a fast neutron to make sure that it's able to slow down to a thermal energy, it's actually more likely to happen in the heterogeneous configuration where I have so much more moderator space for that thermalization to occur. So for this one, it would be the heterogeneous. The heterogeneous system is going to allow for more moderation. And it's also going to allow for less, it's going to mean that there's less parasitic absorption in the fuel too, because I have neutrons more able to get to thermal energies where they're outside of that resonance region, where the resonance absorption in the fuel would be high. So if I get better, if I get more thermalization, if I get more neutrons slowing down to thermal energies in the heterogeneous configuration, that means that the resonance escape probability in my heterogeneous configuration is going to be larger than the resonance escape probability in the homogeneous configuration. So P for a heterogeneous configuration is going to be larger than P for the homogeneous configuration. These things are explained in, like in Svekhov's notes, he does these explanations too. His explanations are a little bit different than mine. So if what I'm saying is kind of seeming strange to you, or if it's not making sense, taking a look at the definitions in the book, it could be that the way that the book explains it is like is done in a better way. But so that's the conclusion. So that's the conclusion about the resonance escape probability. For a heterogeneous system, it's going to be larger than a homogeneous system. The next one is thermal utilization. We can think of that as being like the total number of neutrons absorbed in the fuel divided by the total number of neutrons absorbed in general. So for a hetero system, the main difference is that there's going to be spatial self-shielding. That if I have let's say I have a neutron that's like born fast in the fuel, that neutron is most likely going to end up in the moderator. Once it's in the moderator, it's going to have all these different scattering collisions. It's going to kind of bounce around and be interacting with these moderator atoms until it's slowed down enough that it can go back into the fuel as a thermal neutron and cause a new fission. If I have a heterogeneous system, then there allows for spatial self-shielding such that some of the neutrons, like maybe if I have an intermediate energy neutron, it's going to be shielded by the outer atoms of the fuel. And inside of the fuel, like in the center of the fuel, I'm not going to have as many neutrons in like intermediate ranges reaching the fuel in the heterogeneous configuration because of that spatial self-shielding. So if I think about what's happening in the heterogeneous system, that's kind of the picture. In the homogeneous system, the fuel is uniformly distributed everywhere. So it's like any neutron moving around kind of has like an equal chance of seeing a neutron, or sorry, any neutron moving around has an equal chance of seeing a fuel atom. So if we think about there being more self-shielding in the heterogeneous, if we think of there being more self-shielding in the homogeneous case, where I have fuel atoms in the center of these fuel elements that aren't really seeing any neutrons at all, what do we think is going to be, which case? So, so in which case do we have, shit. So in the heterogeneous case, what we're saying is that because of this self-shielding, there's ultimately going to be less absorption in the fuel. We have less absorption in the fuel because of self-shielding, because of neutrons getting absorbed in the outer part of the fuel before they even see the inside of the fuel. So it's almost like, if you think about the heterogeneous configuration, it's like the center of each of these fuel pins has fuel that neutrons aren't really seeing. So whereas if it's a homogeneous system and the fuel is uniformly distributed, then there's no self-shielding and any fuel atom is going to be able to see neutrons kind of with equal chance. So if the heterogeneous system has less absorption, that means that the thermal utilization in the heterogeneous system is going to be less. So here, the thermal utilization for a homogeneous system is going to be bigger than the thermal utilization for a heterogeneous system. And hopefully that makes sense if you just think about the fact that some of the fuel here is just not really going to see any neutrons because of self-shielding. Hopefully that makes sense. And then the last one that I wanted to talk about was the fast fission factor. So the way that we define the fast fission factor, we had that equation, but in that equation we had P. And so if we want to define the fast fission factor, the definition has to be consistent with our definition of the resonance escape probability. So we are going to redefine the fast fission factor for a heterogeneous system. And the argument is that we're going to assume that at some E0, let E0 be some energy below 1 keV. Well, if we're below 1 keV, we're not going to really have any fission neutrons that are born at that energy, right? Most fission neutrons are born fast. So if we say at E0 of 1 keV, we can make the argument that most neutrons aren't born below that energy. Also, if that's our cutoff, it's very unlikely that a neutron gets to that energy by only scattering with fuel, because the fuel atoms are so large, neutrons aren't going to lose much energy in an interaction with a fuel atom. So if there is a neutron that has energy below that cutoff, the reason that it got there is probably because it was scattering with moderator atoms to get to that thermal energy. So if a neutron has an energy below E0 in the fuel, it likely got there by first slowing down in the moderator. So that's what we're going to say here, that it got there by slowing down in the moderator. So if we think about it from that perspective, then we can recast the fast fission factor as telling us how many neutrons slow down below that energy in the moderator, divided by the total number of neutrons coming out of thermal fissions. So if that's the case, then to say which one is bigger, epsilon for heterogeneous or epsilon for the homogeneous, we just need to ask which one has more neutrons that can slow down to thermal energies in the moderator. Which configuration has better moderation, the heterogeneous or the homogeneous? Hetero, right? And so that means because of the coolant being separate, the moderator being separate, you get good moderation when you're in that region. In the heterogeneous system, more neutrons will get to thermal energies, and therefore that fast fission factor for the heterogeneous system, epsilon for the heterogeneous system is going to be bigger than epsilon for the homogeneous system. So yeah, this thinking about hetero versus homogeneous, it kind of it takes some training of our brains to think about what are the differences. That's what I was trying to illustrate here. Hopefully that makes sense, and that's how we can use that reasoning to explain which factors are going to be bigger or smaller than each other. Oh, question?
Was the fast fission factor of the hetero greater than? No.
Oh, yeah. Yeah, it's bigger. So we wrote the four-factor formula. That eta T was the thing I was saying. It's kind of complicated. You really need to know the full flux distribution to say stuff about eta T. So we're just going to kind of ignore him and say that for hetero versus homogeneous systems, we've already compared these factors. And basically, for the homogeneous case, the fast fission factor is larger. But then for the heterogeneous case, the resonance escape probability and the thermal utilization is larger for homogeneous. The resonance escape probability and the fast fission factor are larger for the heterogeneous. So if we want to say in which case does K infinity go up or go down, it kind of depends on if the offset on if the decrease in F is being offset by the increases in P and E. And it turns out that depends on the enrichment of the fuel, that if your enrichment of 235 is like less than 5%, then these cases that we've just talked about hold. And if your enrichment is above that, everything kind of flips in the opposite direction. So what we're saying is that if omega is our enrichment, if it's less than or equal to 5%, 235U, then it means that the K infinity for the heterogeneous configuration is going to be bigger than the K infinity for the homogeneous configuration. And so that's basically just following what we had said here, that if P and epsilon are higher for the heterogeneous system than F, which is larger in the homogeneous system, that means that overall K infinity for the hetero system is going to be larger than K infinity for the homogeneous system, as long as our enrichments are below 5%. If our enrichments are below 5%, then all of these equalities are true. If the enrichment is above 5%, it switches though. So if the enrichment is above 5%, then the inequality reverses. And then the infinity for the homogeneous system is bigger than the K infinity for the heterogeneous system. So that hopefully helps us understand the difference between homogeneous and heterogeneous, helps us understand which of those terms in the four-factor formula are larger or smaller in each configuration. And then this last thing tells us which K infinity is going to be larger based on our enrichment. Oh, question?
How do we see that?
I think it depends on where you end up going. And actually it depends on kind of where we end up going as an industry because like so most reactors they are LEU, which is like 3 to 5%. Um, but there are folks that are interested in doing things with our fuel to make the fuel last longer. And one of those things is increasing enrichment. Another thing is just increasing burnup. Some and I guess it depends on also what reactor. Like, so those are power reactors, but we use reactors for other things like sorry?
Like for this.
Yeah, using them for research, using them for producing medical isotopes. And typically the medical isotope producing reactors have a higher enrichment. Like I did an internship at Oak Ridge National Lab, and they have the HIFER, which is the high flux isotope reactor. That reactor has been running since like, the early days. Um, it produces plutonium, but it also produces medical isotopes. Its enrichment is like over 90%. Yeah. Um, it's getting there for sure. They have a very cool design with very exotic fuel that you wouldn't see. Like instead of the fuel being in pellets, it's in these weird plates. Look up Hyper. Cool tech.
Outside the pump, is that-
Um, oh yeah, so that would be for like a traditional like light water power reactor. That's the case. But no, this one it's like it's in these weird plates that are almost like bent and it's weird. It's you never seen anything like it.
how-
There's a company BWXT that does they make their fuel. So yeah, it's one of those things where you probably need like all kinds of classified clearances and stuff. Um, so real reactors, if we want to attempt to do this, we got to understand like what's in a real reactor and what would homogenization look like for a real reactor. We were already talking about how like if you have 200 assemblies and each one has 17 by 17 um, elements, then that's going to give you 57,800 total elements. About 55,000 of those will be fuel, and then you'll have other channels for like control rods and instrumentation and things like that. So in your reactor system, you've got multiple regions. The physics involved in these interactions is energy dependent. Um, if we wanted to attempt to do anything realistic with a reactor like this, with these many fuel elements, if you're thinking about like solving it on a computer, for example, you're talking about like an incredibly computationally expensive task. Because like if you want to model each of those elements, like a full reactor core with all of those elements, each of those elements you're going to have to break up into like little pieces. You're going to end up solving like multi-group diffusion equations in each piece. And if you break 55,000 fuel elements up in a computational tool, you're going to end up with like millions of individual like cells that you're solving equations on. So to do like an accurate computational analysis of a whole reactor is a massive computational undertaking. And that's only the neutronics aspect of it. If you want to really design this reactor, you need like those neutronics calculations. It's going to tell you like what's the flux distribution in my reactor and what's the power distribution and things like this. And once I know that, I could send that information to somebody who's doing like CFD and thermal design, and they could figure out like, okay, if this is my power distribution, what's my temperature distribution, and where are my hotspots in my reactor, and what kind of flow distribution would I need in my reactor so that I'm making sure that I'm not getting hotspots where I don't want them. And so real reactors are complicated, they're big. We would need like some pretty sophisticated computational tools and approaches to model them. Ideally, what we want is a way to model something that's computationally efficient, so it doesn't take like weeks and weeks and weeks to get results, but it's also accurate in that, maybe it only takes us a day or a couple hours to get results. We want those results to come fast, but we don't want them to be inaccurate. We want to still be able to use something with them. Um, so if you want to do like this detailed heterogeneous treatment of your reactor, it kind of depends on the purpose of your design. Like, are you doing it for homework? Are you doing it for your job? Are you doing it for a senior design project, which is like somewhere in between? That's going to tell you like how accurate do you need to be. The type of reactor too is going to influence how complex your solutions are. And in general, what we're going to do with this heterogeneity treatment is find a way to take our large, complicated reactor, get some average of our constants, like get group constants, like get group diffusion coefficients, cross sections, new Fs, all of that sort of stuff. Get those for each region. And basically, once we had cross sections that were properly averaged over each region, then we could do like diffusion calculations, get the corresponding flux distribution, and do things like that. So like when you're solving complex problems, you basically, as the complexity of the problem goes to the right, you need more time to solve those problems. At a certain point, the problems get so complicated that doing like analytic and deterministic stuff becomes like time prohibitive. And that's why people like tools like Monte Carlo style tools, because they allow you to kind of more efficiently solve very complex problems. So whenever you hear people talking about like using MCNP to do reactor design, this is why that those Monte Carlo style approaches end up being more time efficient than like doing a detailed like diffusion calculation on every part of my reactor. Um, so I think I had a couple more slides to basically just talk about getting us into how we would actually do homogenization of a reactor core. This is mostly going to be relevant for um, this is mostly relevant for our reactor design project, and I actually had some more slides prepared to basically introduce the project. I was assuming that I was going to get through these last couple slides today, but I don't have enough time and I don't want to rush it in 2 minutes. So I think we'll just stop at this point right here, and then when we come back on Tuesday, I'll finish up with these slides and I'll spend the first probably like 30 minutes of Tuesday's class talking about these slides and talking about the reactor design problem. Question?
Slide. And also, how would you recommend us to go through with the project is Python for that or
Python or MATLAB. I did it in Excel, so like if you want to be a degenerate and do it in Excel. Sorry? Gotcha. Another thing that I would recommend if you are doing it in Python is like do it in Python, but also do hand calculations, or maybe even like do the first couple calculations in Excel, or like do some kind of thing to make sure that the numbers you're getting in Python match the numbers you would.
stuff. It's really hard to do it.
Yeah, it's one of those things where it's debugging, and it kind of takes some steps to make sure that we're yeah, being careful about how we're setting things up.
Oh,
And
we need to ask questions on how to set things up because I felt like Cyclovo was really bad about trying to let us know how we're supposed to do it.
I'm gonna try, yeah, so on Tuesday, I was gonna prepare basically slides to just talk about the project, to tell you about like my recommended approach. I was gonna help you understand like what most of the equations you would need, and then
Last time I got like a Richmond's like 0.005%.
No, that's too low.
Figure out.
But yeah, to answer your question, I will try to get you guys at a good starting point, and then I gave it early so that we'll have a couple. So after this point, we're done with the 5th week. So we're like over about halfway through.
Roll that to be able to know everything we're needing now.
Yeah, and we'll have time, we'll have help sessions and stuff like that, so that if we have questions as we go, we'll have time to get those sorted out. My main advice would be like after Tuesday, when you have everything you need, try to start sooner rather than later, so that as you inevitably have questions, we get them answered, not last minute. Related thing, I don't know if y'all saw, I sent an email out yesterday that had I was letting y'all know about the slides from today, but also a little survey, it's like an unofficial evaluation. If y'all have seen that and you could take 5 or 10 minutes of your time to fill that out for me, I would really appreciate it. I don't know if I mentioned it like on the first day, but I want to be a professor, and so this is really important to me. Doing a good job is important, but also making sure that like if we have issues or complaints or anything like that, letting me know about that stuff so I can hopefully adjust, if not this semester, then just moving forward in my career.
You're better than like 75% of professors I've had over there.
Yes.
Definitely better than stuck up with the bar's not really.
I appreciate you saying that. Thank you.
Do you have any tools that you'd recommend for like relearning Python? Because I haven't used it since freshman.
Maybe just do it in Excel.
Yeah.
I'm not very good at Excel, you know.
Because I was gonna like, there's always a learning curve to stuff, and so like if you're starting something and you're like concerned about using the tool, you know, whenever I took this class as an when I took this class as an undergrad, I was in the same boat. I was like, I don't feel comfortable with MATLAB. I did the whole thing in Excel. It's fine. Like, and yeah, I would say so too. I don't even know how you would do that.
Excel isn't pretty bad to like up on. Usually Google can be like, okay, how do I do
The only
this?
real trouble is like learning the shortcuts, but you don't really.
If you want to do it in MCMP, I'll give you bonus.
I'm kidding, I have
Same.
no idea what.
Oh, I
Actually,
see.
I've got a friend who took the class, I might ask him.
'Cause- And
Yeah, she really. tries
Said do it all whenever you want, as long as you show them. Oh, no, I was thinking like, I prepared for something. So.
Certification, not like.
But yeah, so like to answer your question, to the extent that you have coding for this, it's not super like the most complicated stuff is like loops and like linear algebra.
The matrix, putting something.
Yeah, it's probably almost harder to just set up the matrices than it is to like actually, you know, once you have like your L matrix set up, then you're just doing the inverse of that matrix times your chi vector to get all of your group flux components. So
The derivations of the project.
there is just a little bit of it's not really derivations, but it's like I am asking for like kind of a report where you do like an intro, a methods and materials, and then the methods just like outlining like these are the governing equations, these are the this is like the overall approach,
I read
these
through
are
it
the
a
assumptions.
lot better.
And hopefully it's, yeah, I don't remember. I kind of, I took 601, which is grad reactor
Yeah.
theory, and they use the same project with just some extra stuff at the end.
Everyone just reads
um,
their spec. Spec awesome.
So I basically reused his, and so yeah, hopefully
Oh, so it's a grad level.
it's really, no, that was the funny thing, is that it's the same project. The first part is the exact same, and then in the grad level class, we cover basically everything we've covered in this class, plus a bunch of like heat transfer and fluid and thermo. And so the end of the project is like you do all of the neutronics design, and then from the neutronics design and knowing like your flux profile, you also get a temperature profile from doing like the heat transfer calculations. So to the extent that it is the same, yeah, so it's the same as the undergrad version. And so yeah, not expecting y'all to do any grad level heat transfer stuff. But yeah, so
Yeah.
if we have time, that's
Yeah, it's same design, yeah, it's, you have. I have where, yeah, where, oh, I've got a. I got a note.
Okay.
That's why we're late. Was the one we took a quiz or something?
Oh, gotcha. Yes, yeah, we do.
All ADMs, like.
Do you want to just take it real quick?
Yeah.
Yeah.
I'm so happy about that.
And it's my first semester living on campus too.
I mean, could I take these like later?
If you want to wait, you can. You just have to kind of do it on your own time. So like if you want to take it, not today, just like shoot me an email letting me know like when to expect you. Like if you're gonna do it after class, you don't need to shoot me an email, but if you wanted to do it like another time, outside of like around class hours, just let me know. And if I need to like come to campus, yeah.
I'll probably do it after the next class.
Okay, yeah, sounds good. That would be fine. All right, you're welcome. Hey, James.
Have